Hi, everyone. Today we are talking about the cross product. This is going to be our first video leading into angular momentum. So in physics, when is a cross product superior to a dot product? So dot product and cross product are two different ways to find a vector product, but they have one key difference. Okay, so when we did a or a dot product, right? Remember, I dot I, right? That is your max value, right? If your vectors are parallel, then that's your maximum, right? It also uses cosine theta, and when you use cosine theta, theta of 0 is 1, meaning that that would be your maximum or your ideal, right? However, to get your maximum in a cross product, you would use something that is perpendicular. Okay, that is your max because it uses sine theta, and sine of 90 is 1, meaning that that would be your maximum value, right? So in physics, a cross product would be superior to a dot product if what you're if the vectors that you're multiplying need a maximum efficiency or a maximum value at 90 degrees at a perpendicular angle rather than being parallel. So for example, which of these quantities is calculated with a cross product? Well, work, that is a dot product, right? That is R dot F. Torque is a cross product. That is R cross F. And angular momentum is a cross product as well. That is R cross momentum. Okay. So we've got one's the dot, and then we've got two that are cross products. Now, we've talked about the right-hand rule before. Okay, use the right-hand rule to draw the connection between the force that causes torque and the direction of torque. It may be weird. So the right-hand rule is important here. Now, I do want to emphasize that in dot product, you can say that R dot F equals F dot R, right? We never really talked about the order of the components when we talked about the dot product, but in the cross product, okay, if we're talking about torque, R cross with F does not equal F cross with R. So that's why we are going to use this ordering when we talk about cross product, okay, because they are not the same. And we can use the right-hand rule to figure this out. So the right-hand rule you can either use just with your fingers or you can use your entire arm, okay? So I'm going to do it relative to myself, but I will use terms so that you can mimic this, okay? So the right-hand rule, you use your pointer finger for the first term. So this will be our radius, and then your middle finger will be the second term in your cross product. This will be our force, okay? And your thumb is going to be your resultant, okay? So you have an XYZ coordinate system here, right? Now, if you have the radius, that's your pointer finger, and then the force going in perpendicular, then the torque is going to show you the axis, right? That's along this new axis that we're talking about when that torque causes rotation. So that'll show you that force is causing torque and the direction of the torque. Now remember, torque is in a plane perpendicular to the XY or to the RF, right? That is simply to show, and I can actually show that, whoops, right here, right? This is an example out of our book. If you have R, and then you can see that F is ever so slightly off, then point your thumb, and that will be the torque, right? You can also see that R, F, if you have your R and F in that orientation with your pointer finger R and middle finger F, that if you follow that force relative to you, right? Don't don't worry about my video. This might be backwards for you. But as you do that, that's going to show counterclockwise rotation, right? So if that thumb is our torque and it moves counterclockwise like that, that is positive torque, right? We talked about how torque is positive counterclockwise and negative clockwise, right? So you can also use your arm. This is a little bit harder to do, but if you use your arm as the radius and your fingers, I use all four fingers as your force, then your thumb, stick out your thumb, that will show you the direction of the torque. Okay, I prefer the right hand rule, but remember cross product does matter what order you are doing those in. So your pointer finger has to be the first term, middle finger has to be the second term, and you don't want to like switch these up. Okay? Keep it natural. And it's hard to say that that's natural, but it's a whole lot more natural than trying to do that and flipping someone off, right? So keep it natural, keep it appropriate. So that is how the right hand rule can help you draw the connection between force and torque. Not literally draw, but make the connection. Okay. Now, number 4 says if A and B are parallel, what is A cross B? Well, if A and B are parallel, A cross B would be 0. Okay. A parallel to B, A cross B is 0. Okay. B cross A would also be 0. So that is one case where they would be the exact same. Now, if A is perpendicular to B, A cross B is simply the product of the absolute value of A and the absolute value of B. Now, can we graph the cross product? We can. So here, we can see that, say this vector right here is our radius. Say that's our position vector R. Okay. Let's say that's R. And let's say that this is F. If you make another F over to this side, parallel to the original one, and you make an R parallel to the original one here, you make a parallelogram. Okay? If you have the area of that parallelogram, that would be your cross product. Okay? So finding the area of that parallelogram would be how we did this graphically. Right? This image also shows that A cross B does not equal B cross A. Okay, so I'm going to use the custom that positive X is to my right, positive Y is up, and positive Z is towards me. Okay, so use the same for yourself. If we say that our pointer finger, just for natural right-handedness, our pointer finger is going to the left and our middle finger goes down. Okay. Now our thumb is pointing at ourselves. Okay. That is negative I cross negative J is positive K. Okay, that's what we just did. Now, if we were to do that backwards, instead of negative I cross negative J, let's do negative J cross negative I, but that negative I needs to go to the left, right? So this gets kind of weird, but your negative J, negative I, now your thumb is pointing away from you, whereas before it was pointing towards you. Okay? So that just shows that it is the opposite, right? It is the negative. And we will actually use that concept to manipulate our negative values and to know what is positive and what is negative when we're doing cross product. So those very important relationships. Okay. All right, so that's how we can introduce the vector product or the cross product. We'll continue on to do a couple examples. Okay, so let's sketch a 3D coordinate system and label the positive X, Y, and Z axes. So kind of hard to draw in 3 dimensions, especially if you're a favor of straight lines. Not great at straight lines. And then we have, okay, so this is our positive x, positive y, positive z. You can also say that this is your positive I. This would be your, positive j. And this would be your positive k. Okay, so we're dealing with those unit vectors, right? Now, use the right-hand rule to find that I cross j equals negative j cross I. So let's do that. Okay, this is going to twist your wrist in silly ways, but we have positive I to the right. Okay, this actually might be easier with your arm. Positive I to the right, positive j is up. That means that our thumb is pointing what should be towards us, right? If you have, right? Like that, right? I to the right, j up, k towards you. Okay. Now, if we do negative j is down, right? Like we have on our image, negative j is down. Positive I is to the right. Now our thumb is also pointing at us. Okay. So that means that on letter A, this equals positive k, right? Next, we have positive j crossed with k. So positive A is down, positive k is towards us, right? No, I'm sorry, positive j is up. That's why that's not working. Positive j is up. Positive k is towards us. So your thumb now points to the right, okay, which would be positive I. Now we have negative k. Negative k is is away from you. And yeah, that's right. So j, k, I, then you have negative k, j, and then I as well. Okay, so these both equal positive I. So we will put that down. That is positive I, right? Now we have k towards us, I to the right, so your thumb is pointing up. Or you can say that negative I is to the left, k is towards you, j is up, right? So there's a difference between that and that. But both times our thumb is pointing up, meaning that that would equal positive j. Okay, so I cross j is k. J cross k is I. K cross I is j. Now, one way to remember this, so this is something that I believe we had a student do this before, but it's called the Thurston assertion circle. So if we have I, then we have j going clockwise and k. If you go clockwise, your cross product will be positive. Here, you know what? I'm going to color code this to make that easier. Let's say that clockwise here is positive and counterclockwise is negative. Okay. So if we follow the green line, I cross j becomes k, right? Clockwise. Then we have j cross k becomes I. Then we have k cross I becomes j. Okay. Now let's do it backwards and show that we're right. If we do I cross k, you get negative j, right? Just like how k cross I is positive j, I cross k is negative j, k cross j is negative I, and j cross I is negative k. Now, if you wanted to do this to keep counterclockwise positive, because that's kind of how torque works, right? Then we could move these around, right? What we could do then, if that's going to help your brain, then you could do that. And then we would say that the green is negative and the red is positive. Okay? So if you have I cross J, you get K in the red, right? Then you have J cross K, you get I in the red. Then K cross I, you get J in the red, right? Then green going backwards, you would have I cross K is negative J, K cross J is negative I, and J cross I is negative K. I like that version better because it keeps counterclockwise as positive. So I'm actually gonna redo that for my curriculum, and that was a good idea. All right, now what is the value of I cross I, J cross J, and K cross K? So all of these are 0. Okay? I cross I equals J cross J equals K cross with K. Okay, these all equal 0 because I is parallel to I, J is parallel to J, and K is parallel to K, right? You can think of this in torque terms, right? If you have a force that is acting in the same direction as the radius, you're not going to get any angular acceleration, right? But if your torque starts operating at a 90-degree angle, perpendicular to your radius, then now you're going to get some angular acceleration. So cross product encourages perpendicular, and dot product encourages parallel. Now let's use some numbers. So a particle at position r equals I plus 3j plus 0k meters is subject to a force of 3I plus 2j plus 1k newtons. Draw the position and force vectors as best you can. So this gets kind of tricky, okay, but that's a little bit better. So our vectors, I'll use blue for R. We have 1I plus 3j, so that is, it's 1I plus 3j. Okay, you know what? I don't know if I'm going to be able to do that. Let's see. Nope. Let me just undo this, and I'll do this again dotted. So we'll have 1I, 3j. So that is our R vector. Now our F has a K component. You have 3I plus 2j plus 1k. So here I will use red for force. We have, 3I. So 1, 2, 3. 2j, right? 2j. We'll call that 2j. And then 1k. I'm going to make that parallel with my j-axis, or k-axis. So that means that this is a three-dimensional vector, kind of hard to imagine, but imagine that, that k dotted line is coming out of the screen at you a little bit. So that is your force, okay? Now, draw the position and force vectors. We did that. Calculate the torque about the origin. So let's show you how to do this math, okay? So if torque is R cross F. Now, how to find this? What we do is torque is going to be in terms of I, J, and K, right? In terms of Newton meters. However, to get our I, we are going to take the J of the radius, and we will multiply by the K of the force. And then we're going to subtract the k of the radius times the j of the force. So you take j times k minus k times j, and the r always goes first, f always goes second. Okay. Now for j, we take k cross I. So you have k of the radius, k cross I, minus I cross k. And then for k, you have I cross j. I cross j minus j cross times the I force. Okay, good. So that's how you can do the cross product. You multiply. So for I, you get j cross k, right? But you take the j of the radius times the k of the force minus the k of the radius times the j of the force. So let me get those vectors over here so that we can use this. R equals 1I, 3j, 0k meters. And F was 3I, 2j, 1k newtons. Now, let's do this math. Let's power through this. I'm going to show you an easier way to do this on the next slide, but this is how the math works out. I'm going to show you a way to draw it if you're a visual person. So we have the j for the radius is 3, k for f is 1, then minus k for radius is 0, times, it doesn't matter what the j is for f. So you have 3 minus 0 is 3. Okay, 3i. Now for j, we have k of the radius, 0. I for f is 3, don't matter. Then I for the radius is 3 times k for the force is 1. So you have 0 minus 3. Now you have negative 3j. Okay. Messed up. Hang on. Let me redo that one. So k for the radius, 0. I for the force, 3. I for the radius was 1. K for the force is 1. There we go. That's right. Negative 1j. Now for k, I for the radius is 1. J for the force is 2. Minus j for the radius is 3. I for the force, 3. So we have 2 minus 9. So 2 minus 9 is negative 7. Okay. All right, so our torque vector looks like it will look like a 3i minus 1j minus 7k Newton meters. So that is calculating the torque about the origin. So that also means that if we were to draw this, right, we would go 3, 1, and then 3, 4, 5, 7, way off this way. Okay. So that looks like a negative torque, right? Right-hand rule, also if we have, so if we have R cross with F, so we should get something that's a negative torque on that one. Right-hand rule can confirm the negative torque, because that's going to want to go clockwise. Now, what changes if the axis of rotation is at 0, 6? So before, our axis was about the origin, right? We assume. Right? All right, so we are going to now find what changes if the axis of rotation is at 0, 6. So before, our axis was at the origin. This time our axis is here. So now we have the position doesn't change, but now its relative vector changes. So we were at this point here. Okay, that was our R. And the vector to describe that was I3J, right? To go to the right one and up 3. But now you will go to the right one and down 1, 2, 3. I missed my origin. Didn't count that right. So instead of going right 1 and up 3, now you'll go right 1 and down 3. So now the R vector is I minus 3J plus 0K meters. Okay. So this is how this is going to change if we move our origin. Now for the force is not going to actually change, because the force is just acting on the position, right? So the origin is affected, but the force is not. So now if we were to do this again, the right-hand rule can confirm that this would now be a positive torque. Because now, if we use our right-hand rule, okay, you've got, now instead of I plus 3, you have I minus 3, and now your force is coming, let's see. Yeah, your force is still coming off that way to the right and kind of a little bit at you. So now the torque is still positive, or the torque is now positive. Whereas before, when the radius was pointing up and the force was in that direction, torque pushes away from you, so that should be negative, right? But now we have this scenario going on right here, right? And if we did that math, let's see what that would change, right? The only thing we changed was the J to -3. So anywhere that we see this guy would be a -3. So wherever there is JR, okay, JR and JR. Okay. So those are now -3s. So this is a -3. And this is also a -3. So that gives us a -I, -3I. And this would, instead of being -7, that would become 2 plus 9. So that would be a +11 instead. So you've got -3, -1, +11. So that's going to drive your torque to be positive. So this is how you can do this using numbers. Now the right-hand rule is going to be the best way to figure out if that torque is going to be positive or negative. And we'll actually do the matrix in this next problem. It makes the math a little bit easier to follow. So the determinant matrix, okay, we've got a force of 2I plus 3J newtons is applied to an object that is pivoted about a fixed axis along the z-axis. If the force is applied at point 4I plus 5J plus 2K meters, find the magnitude and direction of the torque vector. Draw the diagram. So what we'll do here to draw this diagram, I'm actually going to do this down here. So we have R cross F, right? So if you have R cross F, if you want to do the matrix here, this makes it a little bit easier. You have your R vector, and then you have your F vector. Okay. So our R is 4, 5, 2. So you have 4I, 5J, 2k, and I go ahead and draw the I again, and I'll explain why in a second. Then force is 2i plus 3j. 2i, 3j, 0k, and then 2i all over again. Okay. Now to do this, we want the magnitude and direction of the torque. So let's find the vector component first. So for the torque, okay, if you want your I component, right, I is j cross k, right? I is j cross k. J is k cross with I. And k is I cross with j. Okay, now this is how this is going to work. I am going to color code these. So our I is j crossed with k. So you do j, 5 times 0 is 0, minus this j cross k, right? So you do 5 times 0 minus 3 times 2, minus 6, and that is your I component. Now our j, this is why I wrote that I a second time, because you take your k cross I, and remember you always start with the radius. We talked about that, darn it, talked about that up here, right? Here is your R always going first. R always goes first. Okay. So when we come down here, we start with the R. Let's see, for J, we're doing K cross I. So we'll start with the R, K cross I. Right, so you have 2K times 2I. So you have 2 times 2 is 4. And then you have radius times force again, 4 times 0, which is 0, and the J. And then for K, now you have that. So that's why I have this extra I here, right? Because it makes the crossing a little bit easier. Now for K, you do I cross J, so 4 times 3 is 12. Then you subtract 5 times 2, which is 10. Okay, right? Okay, so if we do this math, our torque should equal negative 6I plus 4J plus 2K. And that is all in Newton meters. Okay. So you've got negative 6I, 4J, and 2K Newton meters. So this is the Determinatrix method. And I'll do this again real quick just to show you how I did that. For the I, you take J cross K. Right? We're using this guy right there. So J cross K, you take the radius, J cross K, minus the radius, K cross J. Okay, you always start at the top. Start with your first one. Cross product matters the order, right? So you have to start from the top. Now remember, multiplication doesn't have any real order. So if we look at this, right, let's do this again. If we do 5 times 0 is 0, minus 2 times 3 is 6. If we said that is 5 times 0 is 0 and 3 times 2 is 6 instead of 2 times 3, it doesn't really matter. What matters is your order of your multiplication, right? It has to be J to K first, then K to J. Just like when we move to the next one, we do K cross I. K to I first, then I to K first. Then for the next one, I to J first, then J to I first. But you can't go backwards and do F to R. You got to do R first. This has to be your starting point on your crosses, if that makes sense. All right, now that was not the actual question, though. This is just, I feel the easiest way for me to do the cross product. I just write it out and I do that multiplication there. Actually, what I will usually do is I will write out my vector. R is 4, 5, 2 meters, and my force is 2, 3, 0 newtons. And I'll just do the crossing in my head, just thinking, okay, they're there. Then I would have to do an imaginary cross there, and I would do imaginary cross there, right? So that's how I would do that if I were doing this problem, if that helps you. Now, it did ask us for the magnitude and direction. So we have a three-dimensional vector. We need the magnitude. So the magnitude of our torque is the Pythagorean theorem. We've got 6 squared plus 4 squared plus 2 squared. All right, so that is 36 plus 16 plus 4, square root that. You're going to get a weird answer. 7.48. 7.48 Newton meters. I wouldn't be able to do that in my head. And then the direction. So this is the tricky part. If you want, and we've done this before. So you have a triangle. Right? The torque is the hypotenuse because it's going off of the axes, right? And then you have your angle theta here, and then you have either your x, y, or z here, right? And you want to find the angle. So what you can do, since you have the hypotenuse, we're going to say that alpha is the angle relative to the x-axis. Beta is the angle relative to the y-axis. And this is lowercase gamma. That is angle relative to the z-axis. Okay, if you're going to give the direction of a three-dimensional vector, you need to give its angles with respect to all three axes. So to find alpha, okay, if you say the cosine of alpha, say we're using this diagram to the bottom, that would be your I component divided by torque. And then cosine beta, okay, that would be your J component divided by the torque. And, whoops, something weird happened there. Cosine gamma would be your K component divided by your torque. So if you want those angles, alpha is cosine inverse of I over torque. So our torque is 7.48, our I is -6, so you have negative. We want to find alpha, beta, and gamma. So alpha would be the cosine inverse of your I over torque. Beta would be your cosine inverse of J divided by torque. And gamma would be your cosine inverse of K divided by torque. Right? So this would be the cosine inverse of -6 over 7.48. This would be the cosine inverse of 4 divided by 7.48. And this would be the cosine inverse of 2 divided by 7.48. So to describe the direction, right, we have the magnitude, 7.48, the direction, alpha. Okay, alpha is 143 degrees. Beta is 57.7 degrees. And gamma is 74.5 degrees. So to answer this, our torque, magnitude, and direction is 7.48 Newton meters at 143 degrees relative to the x-axis, 57.7 degrees relative to the y-axis, and 74.5 degrees relative to the z-axis. Now, it then asks if the magnitude of A cross B equals A times B, what is the angle between A and B? So if that were the case, right? If A cross B equals A times B, the angle between A and B must be 90 degrees, right? They have to be perfectly perpendicular for that to happen. Now, what if the two vectors did not have a k value? For example, r equals 5.6 meters and F equals 3.7 newtons. Notice anything interesting about the torque vector? So let's solve that and see what happens. All right, so we have R equals, what is it, 5.6, 5I plus 6J meters, and our force equals 3I plus 7J newtons. So there is no K component to any of this, right? So if we want, let's do this, we have 5I, 6J, 0K, and 5I. Then we have our force is 3I, 7J, 0K, and 3I. Okay. Now, let's go ahead and do the vector on this. Okay, our torque would equal, okay, our I component. I is J cross K. So you have 6 times 0 is 0. Then you have 7 times 0 is 0. That's our I component. Now for the J component. J is K cross I, so you have 0 times 3 is 0. Minus 0 times 5, also 0. I think you guys can see where this is going. Now for the K component, you have 5 times 7, that is 35, minus 3 times 6, that is 18. Oh, math, was that 17? So notice that our torque is 17 K Newton meters. Now, the reason we did this example is because all we're doing here is I cross J, right? There is no K component. So since there is no K component, that means that there is no I component and there is no J component. To get I, you have to do J cross K. If there's no K, then the cross product is 0. If you need a J component, right? J is K cross I. If there's no K component, the cross product is 0. So all you have left is I cross J, which equals K, and that is all we had was 17K. Right? So that was the point of that exercise. Now remember, K cross I equals J, but I cross K equals negative J. Confirm this by writing your own problem using numerical values. Okay? So this was a challenge for my students when we do this in class, and I'm going to leave this for you guys to do this as a challenge for yourselves. Try to prove that K cross I equals J, but I cross K equals negative J by writing your own problem. This concludes our video on the cross product, and we are going to continue on to angular momentum in our next video.